You may have already learned about the three Cartesian unit vectors, I, j, and k, that point in the x, y, and z directions. Maybe you just thought they were three random consecutive letters in the alphabet, like A, B, C, or U, V, W. Maybe you thought they were chosen because they weren't already being used. Actually, the story is much more interesting than that. To learn why we use I, j, and k, we need to learn something about quaternions. I'm Jeff Chasnov, and I'm a professor of mathematics. In this video, I want to introduce you to quaternions and tell you the story of how I, j, and k became the unit vectors of vector calculus. To understand quaternions, we first need a short review about numbers. Let's start with the real numbers, like a half, a third, a quarter, square root of 2, pi, and numbers like that. We know that these numbers satisfy the laws of arithmetic. These are the commutative laws. A plus b equals b plus A times b equals b times A. One law for addition, one law for multiplication. There are also two associative laws. A plus b plus c equals a plus b plus c for addition, and A times b times c equals a times b times c for multiplication. It doesn't matter which additions or which multiplications you do first. The third law is the distributive law, which contains both multiplication and addition. We can say A times b plus c equals a times b plus a times c, or we can say a plus b times c is equal to a times c plus b times c. So either we can do the addition first and then the multiplication, or we can do the multiplication first and then the addition. When we define a set of numbers, we would like them to satisfy the laws of arithmetic, or at least as many laws as possible. It's not too hard to extend the real numbers to the complex numbers. We write a complex number z equals x plus iy, where x and y are real numbers and I is an imaginary number, satisfying I squared equals minus 1. A complex number satisfies all the laws of arithmetic, and contained in them are the real numbers when the imaginary parts are 0. When you extend the real numbers to the complex numbers, you do lose something. You lose the ordering of the numbers. You can't say one complex number is smaller than another complex number like you can for the real numbers. Just like we can locate real numbers on the real number line, we can locate complex numbers in the complex plane. We take the x-axis as the real part of the complex number, and we take the y-axis as the imaginary part of the complex number. University students in STEM majors all learn about the complex numbers because they turn out to be so useful. In 1545, the Italian mathematician Cardano began the study of complex numbers, but it took about another 300 years before they became widely accepted. But enough about complex numbers. What I really want to talk about in this video are the quaternions. A complex number z is a point in a two-dimensional plane, and in the 1800s, the Irish mathematician William Rowan Hamilton tried to extend the two-dimensional complex numbers to 3 dimensions. He wanted to represent a point in 3-dimensional space, which is the physical space of our world. Hamilton's guiding principle was the law of the moduli. Although the law of the moduli is not much used anymore. It's pretty easy to explain. The modulus of a real number is just its absolute value. The absolute value of a real number can be defined as the positive square root of the number squared. The law of the moduli for real numbers is that the absolute value of a times b is equal to the absolute value of a times the absolute value of b. What's the modulus of a complex number? If we place a complex number in the complex plane and draw a line from that number to the origin, we can find the length of that line using the Pythagorean theorem. The modulus of a complex number is just the length of that line. The modulus of x plus iy is the positive square root of x squared plus y squared. The law of the moduli is then the modulus of z times w is equal to the modulus of z times the modulus of w. Now Hamilton wanted to extend the two-dimensional complex numbers to 3 dimensions because we live in a 3-dimensional world. So he tried to write something like t equals a plus bi plus cj, where j is another imaginary number with j squared equals -1. Where Hamilton got stuck was how to define the product I times j and still have these numbers satisfy the law of the moduli. Hamilton mulled over this problem, how to define 3-dimensional numbers. In a letter Hamilton sent to his son Archibald, he wrote, "Every morning on my coming down to breakfast, your brother, William Edwin, and yourself used to ask me, 'Well, Papa, can you multiply triplets?' Whereto I was always obliged to reply, with a sad shake of the head, 'No, I can only add and subtract them.'" It was on the historic day in October 16, 1843, that Hamilton discovered the Quaternions while walking with his wife across the Broom Bridge in Dublin, Ireland. Hamilton's solution was to extend the 3-dimensional numbers to 4 dimensions. Hamilton wrote the quaternion Q equals a plus bi plus cj plus dk, where I, j, and k are all imaginary numbers with I squared equals j squared equals k squared equals -1. What Hamilton discovered was that the proper product relationship was I times j times k equals -1. Now there's a plaque on the Broom Bridge which reads, "Here, as he walked by on the 16th of October, 1843, Sir William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for quaternion multiplication. I squared equals j squared equals k squared equals ijk equals -1, and cut it on a stone of this bridge." Probably the most famous graffiti in the history of mathematics. In 2012, the sand artist Daniel Doyle created a beautiful sculpture of this historic event in the courtyard of Dublin Castle. Using Hamilton's equations, we can derive all the different products of the imaginary numbers. Let me show you on the whiteboard. We're going to start with Hamilton's equations. We're going to assume multiplication is associative, but we will not assume that it's commutative. So we start with ijk equals -1. We don't need parentheses because it's associative. To determine what ij is equal to, we can multiply on the right by k. So we end up with ijk times k. And we multiply -1 by k, and we end up with -k. Then we can do k times k first. So k squared is -1. So this is I times j times -1 equals -k. Then we can multiply both sides of this equation by -1 to get ij equals k. And that's the first relationship between these imaginary numbers. If we now want to figure out what j times k is, we can take ijk and multiply on the left by I. So we'll have an I times a j times a k. We multiply -1 by I, we get -I. Now I squared is -1 times j times k equals -I. And multiply both sides of this equation by -1, and we get jk equals I. And that's the second of our product relations. We have ij, we have jk. We can do some more manipulation and get ki, and what we'll find is ki is equal to j. These product laws are cyclical in the sense that if we draw a circle and put I here and j down here and k down here, if we multiply I times j, we'll get k. If we multiply j times k, we'll get I. And if we multiply k times I, we'll get j. Quaternion multiplication is associative, but I can show you now that it's not commutative. We know that I times j equals k. We would like to figure out what j times I is. So we can start with this second relationship. So we can write it as I equals j times k. And then we can multiply on the left by j to find j times I. So that's equal to j times k. And we can do the j times j, or j squared, multiplication first, and that will give us -k. So what we have is ij equals k, and also ji equals -k. Okay? If we rewrite this, we have ji equals -ij. So we say that I and j anti-commute. When you commute the product, you introduce a negative sign. That's true for all of these imaginary numbers. They anti-commute. If you place I, j, k in a circle and you multiply them going clockwise, you get positive. If you multiply them going counterclockwise, you get negative. If you know vector calculus, this might be starting to look familiar. We usually print the 3 unit vectors in Cartesian coordinates, I, j, and k, in boldface. And the cross product satisfies I cross j equals k, j cross k equals I, and k cross I equals j. These unit vectors also anti-commute. These cross products look a lot like Quaternion multiplication, and they even use the same 3 letters. This is not a coincidence. In the late 1800s, there was a major scientific fight over the use of quaternions in physics. Hamilton discovered the quaternions, but the baton for its support was passed to Peter Guthrie Tait, a famous mathematician in his own right. Arguing against the use of quaternions was the American physicist Josiah Willard Gibbs and the Englishman Oliver Heaviside. James Clerk Maxwell of the Maxwell equations was a close friend of Tait's during their college days. And largely due to Tait, Maxwell made use of quaternions in the second edition of his treatise on electricity and magnetism. The war of words between the quaternionists and those supporting a simpler approach got quite heated. In 1890, Tait wrote in the third edition of his book, an elementary treatise on quaternions, it is disappointing to find how little progress has recently been made with the development of quaternions. Even Professor Gibbs must be ranked as one of the retarders of quaternion progress in virtue of his pamphlet on vector analysis, a sort of hermaphrodite monster compounded of the notations of Hamilton and of Grassmann. Grassmann, at that time, was a well-known German mathematician. Gibbs replied directly to Tate, but we'll get back to Gibbs' comments in a moment. I'd rather start with the more aggressive reply penned by Heaviside. A section of his book on electromagnetic theory was provocatively titled, "Abstrusity of Quaternions and Comparative Simplicity Gained by Ignoring Them." And in his book, he included an article he had written for The Electrician in 1891. Clearly, then, the quaternionic is an undesirable way of beginning the subject and impedes the diffusion of vectorial analysis in a way which is as vexatious and brain-wasting as it is unnecessary. Coming back to Gibbs, when he was asked, "What's the first duty of a physical vector analyst?" he replied in a letter to Nature, "It is to present the subject in such a form as to be most easily acquired and most useful when acquired." How we now learn vector calculus follows the 1913 vector analysis textbook of Wilson, based on the lectures of Gibbs. We can find in this textbook the modern notation and definitions of the dot product, the cross product, and the del differential operator. Quaternions are nowhere to be found, but historically, the dot product and the cross product did come from quaternions. Let me show you how. We start with two quaternions whose real parts are 0. These are called pure quaternions. Let's multiply these two pure quaternions. First, we compute the real part. The real part comes from the direct terms, I squared, j squared, and k squared. Those give us a -1. So we'll have a negative, and then we'll have a ux vx plus a uy vy plus a uz vz. Then the cross terms give us the imaginary part. So to get the I part, we need to multiply j times k. So we have a j times k here, so plus a uy vz. And then a k times j gives us a negative I, so we'll have a minus uz vy. And that's I. To get the j term, we need to multiply k times I, so we'll have a uz vx. And then I times k will give us negative j, so that will be minus ux vz, and that will be the j term. Finally, to get the k term, we multiply I times j gives us k, so that will be ux vy, and then j times I gives us negative k, so that will be minus uy vx, and that's k. This result may look familiar for those that have learned vector calculus. Using modern vector notation, we would write u equals uxi plus uyj plus uzk, and v equals vxi plus vyj plus vzk. I, j, and k are the unit vectors in the x, y, and z directions. Remember all the relationships satisfied by the vector cross products of the three unit vectors. The scalar dot product and the vector cross product in the Wilson and Gibbs notation are u dot v is equal to ux vx plus uy vy plus uz vz, and u cross v is equal to uy vz minus uz vy times I plus uz vx minus ux vz times j plus ux vy minus uy vx times k. So we can write the product of two pure quaternions as the negative of u dot v plus u cross v in the x direction times I plus u cross v in the y direction times j plus u cross v in the z direction times k. The negative of the dot product of our two vectors then corresponds to the real part of the quaternion product, and the cross product of our two vectors corresponds to the imaginary part. So the multiplication of two pure quaternions results in both the scalar dot product and the vector cross product. Gibbs and Heaviside were in favor of dumping quaternions and just using the dot product and the cross product directly. And that is what physicists eventually did. Vector calculus won the vector algebra wars, and quaternions have been sidelined from physics ever since. If you even ask a physics student what a quaternion is, it's likely you're just going to get a blank stare. It's only recently quaternions have made a comeback in computer graphics because they can be used efficiently to rotate objects in 3 dimensions. So the next time you use I, j, and k as your 3 unit vectors, give a kind thought to quaternions and their imaginary numbers. And although now I dot I and j dot j and k dot k are equal to +1, remember that I squared and j squared and k squared used to be equal to -1. I'm Jeff Chasnov. Thanks for watching.